This first one looks like a parabola, so quadratic. This one looks like a growth, so exponential. This one looks like a parabola roughly, so it's an upside down parabola. This one looks like a line, it's linear. This one looks like is that what you said before? You said exponential the last one? Yeah, okay, it's like a decay, so uh-oh. Match each graph with a description. So an exponential function that is always increasing. What's another name for an exponential function that is always increasing? It's a growth, yeah. Which one of these looks like a growth? Is it F? Or is it down? Yeah, F. Hey, Marquise, you know that the principal sent out an email yesterday about hoodies to all teachers? Want to start? No, it's like a fashion statement. An exponential function that is always decreasing. That would be a decay. Which one of these is a decay? C. A quadratic function with a local. Oh, okay. So here we go. Back to the first semester. When you have a max, where should the parabola be facing when you have a max? Don't worry so much about the word local. And actually, local is not even that good of a word yet. That would actually parabolas have what are called global maxes, but that's not that important. It should be a downward facing parabola. Yeah, downward facing, because when you say max, what are you talking about? The vertex, sure. So this would be quadratic function with a local min. Yep. A linear function that is always increasing. How do you know that a linear function is always increasing? What determines what direction a linear function is going? The slope. Very good. So an increasing slope would be a positive slope. So that would be B. And then the linear function that's always decreasing, that's a negative slope, that would be D. Any questions on that page? Go to the next page. Which is the only type of function below that has an asymptote when graphed? Yeah, that's really. I think this year that's the only time we've heard that, because there are other types of functions that have asymptotes, but I believe that's the only one you guys have been exposed to. Would be C. What is an asymptote? A point where your function approaches, a line that your function approaches but never actually reaches. Which is the only type of function that could have a local max? Yeah, B. Like a vertex. Describe the end behavior. Okay, so we've seen this before. But first, let's give them names. What name would go here? Yeah, this would be exponential. If you wanted to be more specific, we can call it an exponential growth if you'd like. But let's just say exponential. This one's quadratic. And this is linear. Who remembers what M behavior referenced when you're talking about M behavior? The arrows. What are the arrows doing? So remember, when you're talking about x going to negative infinity, this means what's the left arrow doing. When you say x is going to positive infinity, that's you're describing what the right arrow is doing. Okay. So what's the left arrow doing on this exponential function? It's going to the asymptote, which is at -3. If you only put that, that's fine. I also showed you guys how to add a superscript, which is to say, since it's coming at it from the top, sometimes you can put a little plus up there, but you don't have to put that. What's the right arrow doing? It's going up to infinity, so positive infinity. Quadratics are easy because the end behavior is going to be both. The same for both arrows. Either both arrows go up or both arrows go down, and it's always going to go to infinity. So, what's in this case? What are both arrows doing? You got positive infinity, positive infinity. That's it. I agree with you, but okay. And you normally have lunch now? Mm-hmm. Try to go to lunch now and see if you can finish lunch, and then just go to regular advisement because it didn't take that long. Here, what's the left arrow doing? It is going to negative infinity. What's the right arrow doing? Y positive. Which is the only function that might have n behavior such that x approaches infinity and f of x approaches 4 with exponential. Because why would the other two of those three, the other two have arrows that always go to infinity for the x, like they're going to go forever up, forever left, forever down, forever right. When would an exponential function be headed towards just a number? If that was the asymptote, right? And Reed gets it. Right. Which is the only function below that might have this end behavior where it'll go left, up. Look at your paper, because negative infinity x is left, y up, and then this is right, also up. So which one would have both arrows? What's the only one that can have both arrows possibly going up? Yeah, only quadratic. Because the other two exponentials and linear, they're going to have one arrow going up and one arrow going down. It just depends on how far up or how far down, depending on the asymptote. Okay, which of these would have, let's see, this is left, this is down, because y is going to negative infinity. This is right, x going to positive infinity is right, and up. So which would have one arrow going down, one arrow going up, but also going forever and ever and ever and ever and ever. Yeah, it could only be linear because with exponential you have to have an asymptote. Either the up or down would have a limit. So this would have to be linear. Which is the only function below that might have in behavior. So that we're going left, down, because y going to negative infinity is down. Then right, and then also down. So have both arrows going down. Only quadratic, because that's the parabola. Caleb, when I start hearing you be quiet, that means are you lost now? Or bored or what? Okay. Later on that you're confused. Okay. Based on this function, identify which description best fits the function. That's not based on the function given. Identify which description. It's like too simple. Like this is, even though you can't see it here, if I were to distribute this x with the x, it would become x squared, right? So which one's this one? What is this one going to be? Yeah, it's definitely going to be quadratic. Okay, fine. I guess if they want to know a local mix, min or max, this would be 2x squared plus 3x, where the key is the first term. That the first term determines the end behavior. So with a positive in front, is it going to be, are the arrows going up or down? Yeah, the arrows are going up. It's facing up. Therefore, the vertex is going to be a min. The vertex, like this parabola would look like that. So the vertex would be a min. Kiara, you following me? If we got B, if you get rid of the parentheses, even without the parentheses, you're still going to have just the x is going to still be to the first power, even if you combine like terms. So what would this be? Actually, you know what? Let's combine like terms. 3 minus 4 is. You didn't have to, but it's definitely going to be linear, right? Now, even though we do not use the words decay or growth to describe linear, like at least not at this stage, but fine. Just think of growth as being a positive slope, and then think of decay as being a negative slope. If you remember y equals mx plus b, so you know where the slope is located. What's the slope of that line there? G of x is equal to negative 6x minus 1. Negative 6 is the slope, so is this a decay or a growth? The next one should be obvious because look at where the variable is located. Where is x located? It's on an exponent. Therefore, this is exponential. Now, what determines whether we have a growth or decay is the base. Since that base is between 0 and 1, is this a growth or a decay? This should be fresh in your mind. We just covered this. This is what we've been covering the last few weeks. Look at D. D also has the exponent, the variable up in the exponent. But now the base is greater than 1. So what's this one going to be? Growth. How about E? It's definitely quadratic, but even though the terms aren't in order, look at what's in front of the square, a -3. This parabola is going to face down. If the parabola is facing down, where's the vertex going to be? If we have a downward facing parabola, where's the vertex? A max. And then finally on the last one, that should be obvious, that's linear because we have the x to the first power. What's the slope there? What's the slope? The slope is 1/2. Do not say decay, because with linear, it's not about whether it's a fraction or not. It's positive or negative. That's a positive 1/2. Don't get that confused with exponentials. Slope is positive. On the one we did before, up here, the slope was negative. Based on, okay, these are going to be important. You're going to want to watch these. When you're given a sequence, these are all sequences, right? How would we know that a sequence is linear?
It goes up.
Yeah, but if only that had a name. What was the name that we gave that? And there's a common difference. Another word for that would be arithmetic. Okay? Arithmetic. How would we know that something is exponential? That is geometric, sure, meaning that we have a common ratio. The one that you do not know is quadratic. I'll show you quadratic. It's real simple. Okay? I'll just show you when it comes to it. Okay? Can we look at the y's here? Because that's the one all the x's. All we have to make sure about the x's is that they're going up in even increments. You can't be jumping around from like 0 to 2 to 8 to 27. Like they gotta be going in order, which all these x's are. But now we look at the y's, right? Do we have a common difference or a common ratio here, or none of the above? There is a common difference here of +4, +4, +4. So obviously this is linear. Okay. Is the common ratio, because the common difference we've made before the analogy where it's like slope. So because this is going up, because the slope is positive, is it a linear growth or decay? But now here we go, perfect. Let's look at the one right next to it, right? You look at that one and you're like, well, I don't see a common difference there. I don't see a common ratio. Well, that must mean it's quadratic. Well, no, you never want to make that assumption. So if you want to know for sure how you get it, here's the way it should work. Treat it as if it was linear. Because of the three, the ones that are most kind of closely related are the linear and quadratic. You know, changing the exponent. And go ahead and take this was called what you just did over here. This is called taking the first difference. So take the first difference. You always gotta remember, keep in mind it's the one after minus the one before. So like, what's 2 minus 1? Yeah, like I went up +1. I went up 1. But then what's 1 minus 2? -1. What is -2 minus 1? -3. What's -7 minus -2? It should be -5. To go from -2 to -7, you go 5 down. Okay. If you wanted to prove that something was quadratic, what should be common is the second difference. You take the difference of the difference, and that's what ends up being common. So let's see here. What's -1 minus, like to get from 1 to -1, what should you be doing? Huh? To go from 1 to -1, you're going down 2. To go from -1 to -3, what are you doing? Going down 2. To go from -3 to -5, what are we doing? Say it again. Going down 2. So you see how we have a common second difference? The second difference is common. So that's what tells you that we have something that's quadratic. What's going to tell you whether it's a max or a min is what that common difference is. If that common difference is negative, that means the parabola will be facing down. So is it going to have a max or a min? Okay, look at the next one. Huh? You just want to tell me the answer? Don't tell me what's the answer. You say growth? I don't see that. I'm not seeing exponential at all. Right? Because if it was exponential, there should be a common ratio. 0 times anything is 0, like, so I'm not seeing where that would be exponential. It can't be linear, so instead of just assuming it's quadratic, let's test it for quadratic. Let's take both differences. What's the first difference between 0 and 2? Say it again. Plus 2. What's the first difference between 2 and 6? 4, and then 8, and then. Huh. Because then this would be 2, 4, and 8. Huh? But it can't be linear because linear would be yeah, the second difference is exponential. Huh. I want you to graph that? Because I'm not seeing exponential because the y's are times 3. Maybe because there's an asymptote, maybe that's what it is. That has to be it. There has to be an asymptote there or something. And we haven't done exponential regressions. Yeah, it has to be exponential. I'm trying to look for the pattern, doing it in my head. I'm getting times 2 plus 2. Like to get from one to the other, it's times 2 plus 2. Like what 0 times 2 is 0, but then plus 2 is 2. 2 times 2 is 4, but then plus 2 is 6. Yeah, so it has to be exponential then. It's just because it's an asymptote. The asymptote looks like it will be 2, but you're adding 2 at the end. So yeah, you're right. And because you're multiplying by a positive 2 to get from one to the next, that's what makes it a growth. If you were to graph it, I guess you would see it also. Okay. This one at first sight looks like it's going to be a parabola, but let's just double check. The first difference here is going to be -3, then -1, then +1, and then +3. 0 minus 3 is negative 3, negative 1 minus 0 is negative 1, 0 minus negative 1 is positive 1. But then when you take now the second difference, it's plus 2, plus 2, plus 2. So because the second difference is positive, it's an upward facing parabola. Which one is that going to be? Quadratic or the min? The vertex is at the bottom. You know, another thing that you could look at, I guess, is, I mean, maybe they don't want me to get this intricate into quadratics. Another thing you could look at is the y values. Notice how here the y values are going up and then they come down. It's a change in direction. They're like a parabola that's going up and then coming down. Here, the values are going down from 3 to 0 to negative 1, but then they go back up like an upward facing parabola. So like for instance here, another way, I guess if you wanted to simplify it, the whole thing with the asymptote, just move everything off. The point I was trying to make to you, but are these numbers all increasing, all decreasing, or is there a change of direction there? They're all decreasing. So they're all decreasing. That means it either has to be linear or exponential. But in order to be linear, there has to be, for linear, there has to be a common difference. That would be the slope. Is there a common difference there? Doesn't appear to be. Because that first difference here is, what is it, negative 32, and then this would be here negative 16, and then this would be negative 8, and then this would be negative 4. So this is going to be definitely exponential, and since the values are going down for y, it's a decay. We won't worry about trying to come up with a progression and figure out what the exponential function is, but we can tell. If you look at it over here, this one, are the numbers always going, are they always decreasing, always increasing, or is there a change? It's always decreasing, but unlike the previous ones, here there is a common difference, which is minus 2. So this is going to be linear. Does that make sense? Did I confuse you guys at all with that third one? Okay. All right, perfect. So now we're ahead again. We're back ahead of. So we'll do as much as we can today. This might spill over a little bit until tomorrow. I think tomorrow I have to give back the test too, right? And then I don't know if we'll have time for the computers, but we've actually done this before. You did it in the first semester. What's another word for that? Slope. Average rate of change is slope. So in order to be able to do this, we need to remember slope formula. So let me write that somewhere here on the board. M is equal to y1 minus y2 over x1 minus x2. Whoa, Mr. Romero. I learned it backwards. It was y2 minus y1 and x2 minus x1. It's the same thing. So find the average rate of change from negative 1 to 2 for each of the functions below. Well, here's the good news. What type of function is a linear? When they ask you for linear, it's just slope. What's the slope there? And it's constant. Slope is always the same for all of those. So this would just be m equals 2. It doesn't matter what the points are. For the other functions, though, we are going to have to substitute. They want to know what's the average rate of change from negative 1 to 2. So we know that these are our two x's. So we just said x1 and x2. These are our two x's. It doesn't matter which one you want to call 1 and 2. Those are the two x's. I have to find the y's that go with it. So I'm going to have to plug in the y. So first, let's substitute here b at negative 1, which would be negative 1 squared minus 1. Negative 1 squared is 1 minus 1 is 0. So one of the points we're going to have is negative 1 comma 0. B at 2 is 2 squared minus 1. But it's 3. So we're going to have also then 2 comma 3. So now I need to go use slope formula with those 2 points. You can do slope however you'd like. I know which way I feel comfortable with. What's the first y I see there? And then the way I teach it is just remember that for the second coordinate, to change the sign. So if my second y, my first y is 0, if my second y is 3, I'm going to write minus 3. Over, what's the first x? Negative 1. My second x is 2, change it to minus 2. That gives me negative 3 over negative 3, which is 1. Okay, now over here for c. First I need to plug in a negative 1. C, plug in a negative 1 would be 2 to the negative 1 plus 1. What's 2 to the negative 1? See who remembers. But 1/2, good. The negative flips it. So 1/2 plus 1, I guess just take my word for it, it's 3. Do you want to see me do LCD? What's 1/2 plus 1 is 3 over 2. You want to see LCD? Let's do LCD. Kiara, do you know that 2 to the negative 1 is 1/2? Do you remember why that was the case? The negative exponent flips the base. Okay. And then how would I write 1 as a fraction? How would you write 1 as a fraction? Right, you would look more cool if you just took the hoodie off completely. How do you write 1 as a fraction? Well, yeah, you could write it as 1 over 1, but thank you. That was a better way of saying it because that way I already have a common denominator. 2 divided by 2 is 1, so that gives me 3. So one of the points I'm going to have is negative 1 comma 3 over 2. Then when I plug in a 2, c at 2, it's going to be 2 squared plus 1. 2 squared is 4 plus 1 is 5. So another point is 2 comma 5. And I'm debating whether I should do fractions because I'm going to really mess with your heads. I'll do fractions. Why not? If you just want to do decimals, 3 over 2 is 1.5 if you feel like it. But I like to live dangerously. So my first y is 3 over 2 minus 5. I'm going to write 5 as 5 over 1 over my first x is negative 1 and then change the second x to negative 2. On the top, what's the LCD of 1 and 2? What is the least common denominator of the number 1 and 2? It is 2. So this stays as 3 over 2. This goes minus 10 over 2. 3 minus 10 is negative 7 over 2. And instead of dividing by 3, I'm going to multiply by the reciprocal, which I'm allowed to do. Dividing by negative 3 is the same thing as multiplying by the reciprocal. Now this allows me to say negative times negative is positive 7 over 6. If you would have used decimals, you would have been in bad shape because you would have gotten a repeating decimal. Which of these functions has the greatest average rate of change over that interval? So which one had the biggest change? And it doesn't matter if it's positive or negative, it's just what has the biggest magnitude. Yeah, in this case it was A, it was the linear one. Okay? But all things being equal, like if you were ever asked about this, if you were to rank how much change occurs in any of these, it goes in order. These tend, if you give it enough space, exponentials change the most normally. This was a very restrictive interval, and also every function was different. Like they didn't really like how can I say this? Like here, this was a y-intercept of 3. This was a y-intercept of -1. That was no, actually, you know what? No, I take it back. It's not. No, the y-intercept doesn't matter. I guess more or less they were the same because of this 2. Here, this 2 was the slope. Here, the 2 was the exponent. Here, the 2 was the base. But if you would have given this more space, if you would have stretched out the interval further, maybe instead of going up to 2, if they would have gone up to like 50, you would have seen that the exponential would have blown the other ones out of the water. All right, see if you can do number 2 there. I want you to do all of them. Find all those rates of change. Luckily, you don't have to deal with the negative here. Okay, we'll do A together because that should be easy. You look at it. What's the average rate of change for A? Huh? What's the average rate of change? What is the slope for this linear equation here? Linear function. Yeah, it's 2. For the other ones, you're gonna have to substitute because that's the slope. When it's linear, you don't have to use a formula. It's just you just look at the slope. Our rate of change is slope. For the other ones, you gotta substitute. You already did it, Ann? Let me give everybody else a minute. Nakai, let me know when you finish. Nakai, you finish? 2. For these 2, you have to plug in. First, I'm gonna plug in a 2 and then a 5. So let's plug in a B for a 2. If I plug in, what's 2 squared plus 2? It's gonna be 6. So 2 comma 6 is a point. Then let's do B at 5, which is 5 squared plus 2. 5 squared plus 2 is 27. So 527 will be here. When I do that slope, 6 minus 27 over 2 minus 5. That gives me negative 21 over negative 3, which is 7. That slope is 7. For the next one, C first at 2. So 2 squared minus 1 is 3. So the point 2 comma 3 is on here. And then for the 5, C at 5 is going to be 2 to the 5th minus 1, which is 31. So 5, 31. The slope is negative 28 over negative 3. That cannot be reduced. So that just gives me 28 over 3. Negative divided by negative is positive. So they want to know which of these had the biggest change. What's bigger, 2, 7, or 28 over 3? If you're not sure, divide 28 by 3. Get a decimal. That's going to give you 9 point something, 9.3. So what's the biggest number? Yeah, the exponential. The biggest change. And this just goes to show you what I just illustrated, which is, if you look at the intervals were actually the same. Okay. How much space is there between 2 and 5? 3 units. How much space is there between -1 and 2? 3 units. So actually the amount of space didn't change, but the thing is that this particular interval was very close to the asymptote. As a matter of fact, x is negative. When we plugged in, oh, I said I erased it. Like you see, the asymptote. Actually, no, I didn't erase it too. Both of these y values, 3 over 2 and 5, are pretty close to the asymptote, and that's when everything kind of compresses on an exponential. But now that I got further away from the asymptote, that's when the exponential function really starts to shoot up, and there's a bigger rate of change. In general, as x approaches infinity, so I mean that as you go further and further and further away, which one is going to grow at the fastest rate? Let's see if I can finish this page. Find the average rate of change between, okay, well, this one's not too bad because they give us a table from -1 to 2. Okay, so here at -1, we have our -1, -3. Is this one? Which one's the linear one? So we can knock that right out. The red, the green, or the blue? Yeah, the green one's the linear one. And what's the rate of change there? 2. So the other ones we're gonna have to find. So -1 goes with -3, and then 2 goes with 6. That one looks like it's gonna be the exponential one. So slope is -3 minus 6, -1 minus 2. Change the sign of the second. These both change signs. So you get -9 over -3, which is 3. And then on this one here, between -1 and 2, so that's -1, -2, and then 2, 5. So the slope is -2 minus 5, -1 minus 2, which is -7 over -3. 7 over 3. Negative divided by negative is positive. Which one of those had the biggest rate of change? What's the biggest number out of all those? 3. Yeah, the first one, A, which I believe that would have ended up being exponential. You know what? They probably, on all of these, they probably wanted us to name it. So this one was named A of X. So I think that's probably what we should have put there, A of X. Let me see, the other ones have names? Yeah. This first one would have been A of X. The linear one. And on the other one, there was C of X. C of X. Yeah. Consider the table below. This was a partial set of values based on the interval provided. Which function always has the larger average rate of change? Okay. So let's just see which one of these is the exponential one. This first one, from -2 to 0 to 3 to 7. Consider the table below that shows a partial set of values for 2 continuous functions based on the interval of x provided on the table, which always has the larger. I don't know about that, but okay. Let's not get too specific. Which one here is getting bigger faster? By the time you reach 2, which one has gotten bigger faster? Yeah, g of x. Find the average rate of change from 1 to 3 for the, okay, I guess we'll do that tomorrow. Yeah. Remind me then that tomorrow we'll start here. We have to do the test, and then if there's any time left, I'll have the progress. On number 6. On which page? On this one here? We're still missing 4 pages? Or did it get out of order? Wait. Let me reopen this. You can see this file is. Let me close this out and let me reopen it. Let's try again. Let's see if the order's off. So, was it this page here? Okay. So now we got to do number 6. Find the average rate of change. Did we do any rate of change? Yeah, we did towards the end, right? We already used rate of change. What's another word for rate of change? Slope. Okay. So of these 3, which is the easiest one to find slope? On number 6. Right now we're working on number 6. Yeah, C. Why? Because on linear functions, slope is constant. It doesn't matter what the interval is. The slope is always going to be the same. So since they give me that function h there, what's the slope of that function? 1, and the rate of change is always going to be 1. So this is just 1. Right, and equal 1. Next week I told you I have a Google form. Remember on the Google form, just put the number. On the other ones, we're going to have to use slope formula. So let's see, when x is 1, see, so on this first one, the exponential one, when x is 1, y is -3. So that's going to be one of the points. When x is 3, y is also 3. So 3, 3. All I have to do is find the slope between those points. We'll use slope formula. Subtract the y, so it depends on which y you want to use first. I'll just use the top y first, so 3. But then change the sign of the second coordinate. So if this is my next y, I'm going to change that to +3 over the x is 3 minus 1. That gives me 6 over 2, which is the average rate of change over that interval is 3. We do the same thing for the parabola. Okay, we have to find the points. The point here is 1, -4, and then when x is 3, y is 4. So slope here, the first y is 4, minus -4 is +4, 3 minus 1, so it's 8 over 2, which is so if you were to be asked which of these actually had the biggest rate of change over that interval? Which one had the greatest rate of change over that interval? In this case, it was the quadratic. But if you learned something from yesterday, if I expand the interval, if I make the interval bigger, especially the more I go out towards infinity, towards positive infinity on the x, the more that I head out towards that way, which one of these should have the biggest rate of change? Exponential. What should have the second biggest rate of change? Quadratic. And then linear is usually the slowest of the bunch. Find an interval of x over which all 3 graph functions have the same average rate of change. Okay. Well, we're kind of stuck here because since one of our functions is linear, like there's only one type of rate of change that one can have. This one here, you're stuck at 1. So basically, what they're asking you here, and I'm not even going to get too fancy on this one. I could get really algebraic with you, but I think I'm going to lose you on that one. So we said that rate of change is slope. What did you learn slope as when you first learned about slope? What's that catchy little phrase that you learned? Now, what's that catchy little phrase that you learned to memorize slope? When you were first taught about slope. Rise over run. Okay? So if you look here, no matter where on my line, the reason why my rate of change is 1 is because no matter where I am, I'm rising 1, running 1, rising 1, running 1, rising 1, running 1, rising 1, running 1 for the entire line. So just to make it simple, can I find any other place on my functions here where I had that same rise and run? Well, yeah, sure. Look on the quadratic, it would have to be there. On the exponential, it would have to be here. Because we're experts on and I'm not gonna write it in this box. Actually, here, let's make our own little boxes. Let's make 3 boxes here, kind of how we have it up there. I like that better. And then in each of those boxes, we'll write the interval where the rate of change is, in this case, 1. Because, these first 2 have a bunch of different rates of change depending on what the interval is, but the last one, the linear one, only has 1 rate of change throughout. So we're stuck. That's what it has to be, because that's the only thing that one can be. It's dragging everybody else down. What is the interval for the exponential one? In between what x's is that rate of change 1? Between where on the x-axis is this rate of change 1? Between 0 and 1. We've learned several ways to write intervals, of which now probably hopefully the most familiar, that's what gets stressed the most, at least in this school, and probably because of the book, is interval notation. So how would I write in between 0 and 1 inclusive? Bracket 0, comma, bracket 1. Not the only way to write it. It could also be written as an inequality, but it's probably easier that way. What's the interval for the middle one, where the rate of change is 1? In between what x's am I rising 1 and running 1? Also 0 and 1. And I guess now that I'm seeing this, it kind of gets me to want to reread the question, because maybe they were just talking about name one interval where they happen to all be the same. And yes, coincidentally, they happen to all be the same in between 0 and 1. So maybe that's what they meant by this. But in reality, if we were to interpret this the first way that I interpret it, which is just, hey, under which even if they're all separate, under which interval do these have a rise and run of 1? Well, under which interval does this have a rise and run of 1? Everywhere. How would I describe everywhere in interval notation? You could say that's what I don't know what you look. You write like ARC, but ARL, but then you tell that. No, I don't know why you always write you write like ARC, like could it be ARN, all real numbers? What? Isn't it you that always writes it on the test? Did you write like AR or something? You just said all real numbers. Maybe let me check. But again, like now that I happen to notice that these first 2 had the same one, that's probably what they meant. Like to find one single interval that just by coincidence these all happen to have the same rate of change, and that would be if this last one has the same rate of change everywhere. Yes, it also happens to have that rate of change over the 0, 1. That makes sense to you? Jason, blink once for yes. All we're doing is finding slope. Caleb? Determine the domain and range. Is this the last page that you have? So determine the domain and range of each of the following graph functions using interval and set notation. Okay, perfect. Let's do both. What's the domain? Well, first of all, let's say what type of fun, and actually, hint, 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 a big part of the quiz on Friday is just going to be naming them. So it's not going to be multiple choice, so please be able to name them like on your own. What type of function is this? Yeah, exponential. If you want, exponential is the key word. Make sure you say exponential. If you say exponential growth, does this have to say your growth? Great, even better. So you don't have to just at least know that it's exponential. Okay, so this is exponential. What type of domain do all exponential functions have? Huh? No, negative infinity to positive infinity. Yeah, so in interval notation, that's what you would write. Negative infinity to positive infinity. How would I write that in set notation? Well, set notation really means that you're supposed to write this like x and that with that. But really, it means you're supposed to use inequalities. So the way that you would write that is supposed to be, well, I don't even know what it is. Negative infinity. Yeah, I'm not going to do infinity. See, like, you guys, pencil, it's easier to write, but it will be x negative infinity is less than x is less than positive infinity. That's how you write it in set notation braces. I have to go back and look at the quiz again, but I'm pretty sure interval notation is going to be the one that's stressed the most. We do have a quiz review set for tomorrow. Usually those quiz reviews are very similar. What's the range here? This is going from -3 up to positive infinity, and it doesn't touch either one, so it'd be parentheses -3, parentheses positive infinity. How would you do that? Remember, set just means, this one I can probably fit here. Y colon braces. Set notation just means use inequality signs. If it's continuous, use an inequality sign. So since this is, and this I've actually done for you. I haven't done it with the braces, but I've done it before for you. Another way of saying this is just saying y is greater than -3. I doubt I would take away points if you forget the braces. But the key is that the inequality has to be correct. Nakai, give me the domain of the next one. What is the domain of any parabola? As taught to you in the first semester. All real numbers. How do we write that in interval? Now, pretty sure it's you, but if you are explicitly told that you have to write something in a certain way, and you write all real numbers, normally I let that slide if you just write all real numbers, but if you're being told to write it a certain way, you have to write it that way. So like if you're told interval notation, you have to know that all real numbers is negative infinity, comma, positive infinity. What would the domain be in set notation? The same thing as it was on this last one. X braces negative infinity less than x less than positive infinity. That's just saying that all the x's are in between those two numbers. It's a different way of writing it. How about the range? Just like with exponential, the range is limited, but instead of an asymptote, what we have is a turning point. Jason, can you give me the range of that parabola that's in the middle? How low does it go? How high does it go? The parabola, we're looking at the one in the middle. Say it goes lower than -2. Yeah, it goes from -4 up to where? Up to where? Yeah, and how would you write that in interval? Well, does it touch -4? Yes, it does. So that takes a bracket, but then positive infinity takes a bracket. Yes, it has to be perfectly written like that. That is interval notation. Anything else is wrong. You need to know that by now. How would you write it in set notation? You write the y, the colon, the braces, and then you would just say the y, but now instead of greater than, because unlike an asymptote, since the turning point actually does touch -4, it would be greater than or equal to -4. And then close the braces. The line should be the easiest thing of all. What's the domain of a line? Yeah, it's all real numbers. What's the range? It's also all real numbers. All lines, as long as they have both an x and a y, which these two, like any line that is diagonal, goes forever up, forever down, forever left, forever right. So in interval notation, -infinity, +infinity, the domain would be x such that that -infinity is less than x is less than +infinity. The range would be again -infinity to +infinity, and then y such that -infinity is less than y, not less than x, less than y, less than +infinity. Did everybody write? Why the long face? Too easy. This next one says graphed, but nowhere in this unit have we stressed graphing. Plus, like this implies that the things are graphed for you, and they're not. But I think we can answer all these questions even without the graph. So, what word can be used to describe a quadratic? What is the domain of any parabola? Every single parabola, the domain is going to be all real numbers. So -infinity, +infinity. I do not need to look at a picture for that. X such that -infinity is less than x is less than +infinity. That's that notation. How about the range? What is the range of any parabola? What is the range of any parabola? How could you describe, generally speaking, what the range of any parabola is? Okay, let me make it easier for you. What does the range of a parabola depend on? Yeah, the vertex. It's either going to be for the vertex up or the vertex down, depending on where it's facing. Can you tell where this parabola is facing? Oh, how do you know it's going up? Because A is positive. So I know the range has to be going up. But going up from the vertex, well, the nice thing is that this is in vertex form. Can you tell me what the vertex is of this parabola? Yeah, don't forget you got to change the sign of the of h there. So it's going to be +1, -3. The more important one, because we're talking about range here, is that -3, that k. Because k is -3, that's the y of the vertex, and I know that we're going up. My range here is going to be from -3 up to +infinity. -3 gets the bracket because the vertex will touch it. +infinity gets a parentheses. Set notation might be easier here. It's just y greater than or equal to -3. How about b? What is b? What type of function is b? Exponential. What is the domain of any exponential function? Yeah, all real numbers. So -infinity to +infinity in interval notation. In set notation, x such that -infinity is less than x is less than +infinity. What does the range of an exponential function depend on? The asymptote. Okay. Now it's either going to be above the asymptote or below the asymptote. What determines that is also a. Remember, 2 is the base. What's the a there? What number's in front of the 2? Is a positive. Yeah, it's a positive 1. So this is going to be above the asymptote. So we're going to go greater than whatever the asymptote is. The asymptote is at k here. So here k is 1. So if I want to say everything above 1, but see the difference is an asymptote you don't touch. A vertex does touch the line, an asymptote doesn't. So now the 1 is going to get a parentheses. Infinities always get parentheses. How would I write this in set notation? Y is greater than 1. Not greater than or equal to, greater than 1, because you can't touch the asymptote. And then finally, C is the easiest because who cares what's there? Well, the only thing that matters is, as far as domain and range goes, what type of function is that? Linear. What is the domain and range of any linear function? Yeah, unless there was an x or a y missing. If it only said x equals a number, or if it said y equals a number, and it only had one variable, then either the domain or range would be limited. But this has both a y and an x, so it would be diagonal. The negative infinity, positive infinity would be both the domain and the range. And then in set notation, x such that negative infinity is less than x is less than positive infinity. And then the range y such that y negative infinity is less than y is less than positive infinity. Caleb, no. You said that you're going to be a good boy from now on. If you're lost, say something. Last 3. If we only consider the functions linear, quadratic, and exponential, which is the only one that could have a range of negative infinity to positive infinity? Linear. Okay, we've seen that we've now done 6 of these. The only one that could have the range go everywhere is linear. If we only consider those 3 again, which is the only one that could have a range of 2 to positive infinity, but look at what's on the 2. It's parentheses, meaning that it doesn't touch the 2. Which one would that be? Huh? Exponential, good. Exponential. And then not by process of elimination, okay, not by default, but if we're talking about range again, which is the only one that could go to positive infinity, but now have a bracket, meaning it touches quadratic. We have now done pretty much that entire packet. It was a 4-day packet, and we knocked it out in 2.5. Are there any questions there? The good news is, like Marmy, even though you've been absent, tomorrow we kind of have a 1-day review of what we've just done the last 3 days. So we pack it all into 1 day, and then we take the quiz on Friday. And then we celebrate on the weekend by studying and doing our homework. Let's see if we can get